Hello everyone, my name is Daniel and I'm a programmer and an artist, and today I wanted to make a video about a new node that I've made for my Strands Geometry Node Assets collection. And what it does is allows you to put a custom mesh, array of custom mesh along all of your strand curves and turn those curves into an object using that custom mesh. So it's very similar to how deform match curves works from my regular geometry node assets pack, but specifically works with the strand system with all of the selection settings, and it also has some additional options that deform match curve doesn't have to be able to put caps on the ends of the curves and stuff like that. So two things I wanted to do. One was just to let everyone know that there is a new version of the Strands library available with this new modifier in it. And then I also thought I'd go a little bit behind the scenes and show you how a Strands modifier works, which could be interesting for several reasons. First of all, just to sort of see how it works and how I put one of these modular Strands modifiers together. And second of all, if you're interested in making your own modifier that could fit in and work with the Strands sort of system that I have, then this should shed some light on how you might go about doing that. So first, I'll just sort of run through some of the settings for the new modifier. You have radius control, which makes the object bigger or smaller around the curve. You have your regular selection setting, so you can choose what strand you want to apply it to. Noise deforms the curve slightly. And then the seed is just for that noise, and also I think it's assigned a random value and stuff. Then the merge by distance lets you merge adjacent vertices, or more than that if you turn it up. Probably leaving it at 0.001 is a good value most of the time, or if you want to not merge vertices, you can set it to 0. This mesh that we're deforming along the curve is aligned with the x-axis, as we can see. If instead it was rotated, this would be along the y-axis. You can choose, depending on how your mesh is oriented, which axis is appropriate. So if we were to switch this to something else, like the y-axis, you could see then it would array them along that axis instead. So x is obviously appropriate in this case. Then there's 3 different objects you can assign. So we have a middle object. You always will want to assign that one probably. And in this case, that's this object here is the middle. And you can choose if that should be stretched or arrayed. If it's arrayed, it tries to fit it to the length. Then the size is applied to all 3 of the different meshes, the caps and the middle part. And you can use it to just adjust the size of your thing globally, what your object that you're arraying. And then the offset for the UVs will allow you to fix seams like this. I know the UVs on this are on the y-axis. Sometimes, depending on how your UVs are rotated, you might want +1 for a perfect tile, or -1 depending on how your UVs are rotated. But a value of 1 will, if your UVs are square, will offset it on whichever axis you want to array along, one size of the UV island, so to speak. And then there's caps to put on the end, so you can choose one object and flip the end. So if you don't flip the end, it looks like this. If you flip it, it rotates it around 180 degrees. So that way you can use the same object for both caps if that is appropriate. Or if you want to have a second object for the other cap, instead you can select that, and then you might not need to flip it. If you want them to be different or whatever, you can do that as well. And that's the modifier. Pretty simple, just a deform match curve, but for strands specifically. All of the strand modifiers, well, most of the strand modifiers, use the same sort of basic structure for how they're laid out. So in a strands modifier, you'll see at the beginning, there's some processing to separate out the part of the input object that we want to work on. And then at the end of all of them, there's some nodes for merging the newly created geometry back into the object. That's what makes it this modular system where you can stack multiple modifiers on top of each other and have them work on different parts and stuff. And then in the middle is all of the custom behavior that this modifier in particular is supposed to do. So in this case, that is taking a mesh, arraying it along an axis, and then deforming it, bending it to fit on the curves it's supposed to be working on. So just to go through this node group as an example, you can see at the very beginning there's this select rope node group, and what it is doing is taking the input geometry, which in this case is just a curve, and it's going to separate it into parts based on the selection parameter. So the selection is the different tags that can be assigned to the mesh. And so inside of this node group, it's that selection parameter is going into a menu switch that outputs a bunch of different numbers. The positive ones are handled in one way, the negative ones are handled in a slightly different way. I don't really want to get into all of that. But then it turns that index value into some kind of a selection based on the rope ID of the curves in the input. And then it will separate the geometry into two parts, the selected part and the non-selected part, and it will take any instances that exist in the input geometry and append them to what's not selected. So essentially you cannot work on instances that will always be not selected, but we want to keep them in the object if there are instances. So then the inverted part of this, what's not selected, you can see here, comes out and runs all the way across the bottom and gets merged back in at the end where there's this node group to append. It's called append control curve, I think, and it takes the original geometry and it pulls out the control curve from that if it's the first modifier in the stack, and appends it to the newly created mesh, as well as anything that was already in the mesh before that was not part of the selection. So if you selected something other than everything here, then that the not selected would have the input geometry, and there'd be nothing in the to custom part. Whereas if you select everything, then there's nothing not selected, and everything gets turned into the mesh. So essentially what we have is a whole bunch of stuff comes into the modifier, and it gets split into what we want to work on and what we don't want to work on. What we don't want to work on just goes to the end of the node group and then gets output at the end. And then what we do want to work on, we make some mesh or do some operation to it in the middle and then merge it back in at the end. Then for all of the strand modifiers, because I wanted them to work on curves and meshes, once we have that selection, this modifier here basically handles the selection input. So once we have separated the rope and we have our selection, we're going to use the separate components node to get both the mesh and the curve parts of the geometry, and we're going to handle both of them differently. So the curve, we want to evaluate the curve so that we turn any points between the control points into actual points, vertices in the curve, so to speak. And then if it's a mesh, we're going to check if the mesh has any faces, and if the mesh does have faces, we're going to delete some geometry called top. That's specifically because there's an option that's sort of hidden that if you want to use cloth simulation on some of the strands, it's possible, but you have to solidify the mesh for it to be able to collide with stuff. And I think that's only done in the sag modifier. I didn't really develop this idea beyond testing phase, so it didn't really get used in the end, but that's why that's there. And then in this case, because we only want to work on curves in this node group, I'm going to turn the mesh into a curve and then join the mesh that was converted to a curve with the part of the geometry that was a curve, which handled, so oftentimes when this is being processed, only one or the other will be true. It will either be all a mesh or all a curve, but whichever way it is, in the end we will have a curve. Then for the main bulk of this particular modifier, which is deforming objects to fit along the curve, we need three primary inputs, and that's going to be our middle object, our start object cap, and our end object cap. Then for the end object cap, there's this special switch to flip it around, and all that does is it rotates the position vector by 180 degrees on some axis, and then we will use that instead of the original. So you can see if you flip it, it flips to the other side because it's being rotated 180 degrees around Z in this case. The rotation axis is determined by this node, which is a switch. If I unhide it, you can see it's just pi on one axis. Which axis it is different depending on what makes sense for the different axis selections. And that is coming from here, where there's a menu switch that outputs 0, 1, or 2, depending on which axis you're selected. So this is a menu switch for this menu, and then that turns into a number here, and everywhere else I care about the axis, I'm going to use an index switch to select a value. So there's a whole bunch of those actually. So there's another one here. This is for our start cap. Once we have the start cap, I'm just going to scale it. So this just takes the position and scales that vector by the scale amount. That's what allows us to adjust this scale value here in the modifier settings. So if we scale this, it gets smaller. And then I want to adjust the object because you can see here that the origin point is away from the object. So to make everything stack up easier or with less fiddling or having to edit origins a lot, I'm just going to move the origin point so that the object starts at it. So we can do that by taking the bounding box of this object, and we can take the min and max values. We want to take the min, multiply it by a different vector depending on what axis is selected. So in this case, because we're arraying along the x-axis, we care about the x-axis, so it's set to 1. The other axes are set to 0. That's again from the menu switch to get the value for this index switch. And then, depending on what axis is selected, we multiply the minimum vector by that axis to remove the two axes we don't care about, essentially, or set them to 0. Then we want to scale that minimum value on whichever axis we care about to -1, and then we're going to apply that as an offset so that the origin starts there. That actually would look like this. And then, because this is the start cap, we actually want the origin to start to be placed at the end of the object. So we're going to take the size of the bounding box, so the max minus the min, multiply it also by that same vector to get only one axis, and then we're going to subtract that from our zeroing vector, which puts the origin on the other side of the object. We do the exact same thing for the end cap, only it gets placed on the other side, and it also then needs to be, after we place it here, we need to calculate how long the middle part is. So if we were to join these two together, you could see that the two caps would be placed end to end, but there's nothing in between them. So after we do the middle part of this, we also need to push the end cap, the distance of the length of the middle array, over. And we can calculate that by taking our axis vector, and we want to scale it by the number of middle parts times the length of the middle part. So you can see for the middle, we are doing the same thing. We're scaling it. We have the bounding box. We're offsetting the minimum so that it starts. We're offsetting the geometry by the minimum vector on the axis that we care about, which is the x-axis in this case, so that the origin point starts here. Before we do that, it starts is placed in the middle. Now we push the origin to one end. And then we also get the size of this geometry, and we're going to multiply that by the axis that we care about, which is x in this case. Then if we take the length of that vector, which is just the x-axis, the x component of the size of this object, we can use that up here to multiply by the number of objects that need to be placed in the middle to get the offset value to move the end cap from here over to the end of the middle array. Then once we have the middle geometry placed here with the origin at the one end, we're going to turn it into an instance with the geometry to instance node, and then we're going to duplicate that instance one time for each curve for each spline in our curve object. So after here at the beginning, where we join our possible mesh input or our possible curve input into what we know will be a curve input for our node group, we're going to set the spline type of that curve to a NURBS curve, and I'm going to set the resolution to 2, which is sort of optional, by the way, but that's what we did here. And then we want to know for a domain size of the curve how many splines there are. And then whatever number that is, we're going to use that to duplicate all of these objects. So the start cap, the end cap, and also the middle, we're going to make one copy of it for each curve for each spline in the curve object. And then for the middle part, we're going to make another copy of all of the copies, where we make a number of copies equal to the length of the curve divided by the length of one middle mesh. So that'll tell us how many copies we need to make to array along the x-axis to get as close as possible to the length of the curve. So the way we can get that value is here. We have our curve that we've deformed slightly with this perturb. That just adds the random noise to it. We're going to sample the spline. We're going to sample the spline length, and the index we want to sample that at is going to be the duplicate index from the copies that we made for each spline in the curve. So that's this duplicate index. The reason there's an add here is just to merge all of the different types together. So essentially on the end cap geometry, this will have a value and it'll be 0 everywhere else. And then on the start cap geometry, it'll have an index but be 0 everywhere else. So by adding all of them together, we get the index value on all of the different parts, the start cap, the end cap, and the middle. So then on all of those different parts, we want to sample at the index of the copy, of the instance copy that was made for that curve, and we'll get the length of that curve. And then if we subtract from the length of that curve the size of the end cap and the size of the start cap, we just handle the case where you have a really big start and end cap, and if you didn't do that, you would squish the geometry in the middle too much. So then once we've subtracted the size of the end cap and the size of the start cap from the length of the curve, we have a value that's the length of the middle part of the curve, if that makes sense. So then we want to divide the length of the middle part of the curve by the length here, which is the size of the middle part object along whichever axis we care about, which is the x-axis in this case. Then that's going to be a number with the decimal place, so it could be like 5.5 or something. We are making copies, and so we can't make half of a copy, so we're going to floor that value to turn it into an integer. So it'll just be 5, or whatever it may be. And then here we handle the case of whether or not you even want to do the array. So if you don't want to do the array, we're just going to make one copy of this, and otherwise we're going to make a number of copies equal to the length of the curve divided by the size of a middle object. And then we're going to duplicate instances again, and we're going to duplicate an amount that's equal to that value we calculated. So now we have what still looks like a middle object, but there's actually like, I don't know, 20 or something copies of it all in the same place here. So now what we need to do is array them along whichever axis we've selected, so the x-axis in this case. So we're first going to realize the geometry, just so that we're working with an actual mesh again rather than instances. And then we're going to scale the size of the middle part on the x-axis, so the same vector we've been working with, by the duplicate index. So that'll be 0 for the first one, 1 for the second one, 2 for the third one, etc. And so what that does is it will stack all of those copies on top of each other, arraying out along the x-axis. So now we have our array, and also at this point I think I talked about it before, but we take that same length and we multiply it by the total count, so the number of pieces that we're going to array along the middle, and we multiply by that and scale the x vector, or whichever axis we've selected vector, by that amount to position the end cap at the end of that middle array. So now we have the array in the middle, we have the start cap back here, and then we've pushed the end cap over to the end of the array. So we have our 3 parts, and they're basically ready to join together. The last thing we need to do is fix the UVs, or edit the UVs on this middle object potentially. And so to do that, I'm just taking, so we take that original middle object before anything's been done to it, and then it comes all the way over here to these attribute statistic nodes. And what we're doing with the attribute statistic nodes is looking at the UV map. We're separating the UV map into the X, Y, and Z components, or U and V components, and we're doing an attribute statistic on the face corner to find out what the min and max values of the X and Y axes, or U and V axes, of those UV coordinates is. And then we're going to combine those together into a minimum XY and a maximum XY vector, and we're going to subtract the minimum from the maximum so that we have the size of the UV space that's used by the UV map, which, if it's square and rotated so that it aligns to an axis, you could then make a copy of. So then we have our inputs, our offset X and Y. We're going to combine those into a vector, and then we're going to multiply our size vector by those offset values. So if you set this to 1, then we will be using 1 size of the UV island, or UV, it's not the island technically, it's the whole UV space, the total bounding box, so to speak, that's occupied by 1 UV map. We are going to multiply that by the factor that we set in the offset, and then we're going to multiply that offset vector by the duplicate index so that the first copy isn't offset at all, and then the second one is offset by 1 times the size of the UV map, and the third one is multiplied by 2 times the size of the UV map, and so forth. Then once we've done that, we take our UV map and we add this offset value to it. So now we've edited the UVs, we've pushed them all over by whatever amount we've set with the UV offset value. And then all we have to do is save that as the named attribute again. So that should be a 2D vector on the face corner named UV map, which should probably be exposed just in case you wanted to edit it. So we'll add that as a UV name parameter that you can edit right there. And we need to copy that to all of these. And then once we've saved that edited UV map, if you've adjusted the offsets, we're ready to join all of those three parts, the start and the end cap and the middle part together so that it's all one mesh again. To be able to deform the mesh to fit along the curves, we need to do two things. First of all, we have our arrayed mesh, and then we also need the curve. So the curve is here, and so all the way back here, after we had both the mesh and the curve types, whatever the potential input was turned into curves, and we sampled all of that. We added some noise to it, and then we measured the length of it. But we also take that curve and run it along the bottom here, and it's going to be used at the end to sample the curve so that we can use the sampled value to deform our mesh. And then the other half of it is the mesh, which we have arrayed along here. But we need to map the length of that mesh onto a factor from 0 to 1. And there's sort of two different ways you could do that. You could measure how big the object is now and then divide the position of a vertex by that amount. Or I actually made this node group to help with that because I was doing it a lot, that takes the position and it just divides the position by that amount, which makes the object fit inside of a 1 by 1 by 1 cube essentially. So I call that normalized geometry. It's probably technically slightly slower than calculating all of the values, but it just makes it simpler because once you've done that, you can just look at the position vector and it will be in a 0 to 1 range, so it'll tell you the factor automatically essentially. So the way this works is we just split the geometry into instances based on this group ID, and that group ID is going to be the curve duplicate index. So all the way back here, we made the duplicates, one for each curve. Those all get added together, and then it runs across the bottom here to the group ID. So then the geometry split to instances, and whichever group ID it is, they'll all be put together. That is necessary because the different curves will be different lengths, and so you'll need to normalize different length arrays into the 1 by 1 cube essentially. Then we don't actually use this instance's geometry for anything other than to measure off of. So this is my bounds at index node. I've shown this node in several other videos, but we're essentially going to take that same group ID. It's going to be our index to sample off of. Once we have the sizes, I don't know why I actually subtract here because I could just use the size, which would be simpler. So we'll do that. But then we take the size and we capture that on the geometry because we will probably want to use it later to restore the size when we put it on the deformed curve. But then if we divide the position by the size, it will pack everything into a 1 by 1 cube essentially. We just use that to set as the position, and the result of that is this 1 by 1 by 1 version of the mesh. Now that we have that, the position of the vertex on the x-axis, in this case, whatever axis you have selected with your aligned axis value, is going to can be used as the factor to evaluate the curve on. So then down here, where we sample the curve, we just take the position, we separate x, y, z. Here, this index switch is, again, for the axis. So if you follow that all the way back, it goes all the way back to that menu switch at the beginning. So if we're using the x-axis, we take the x position, y, we do the y, and z the z. That's going to be output a factor for our sample curve. We also care about the radius of the curve, so that will be the value that we sample. Then we obviously need the position, tangent, and normal vectors to calculate everything as well. Now, if you convert a curve to a mesh, the radius gets set to 0. So here we're just going to accumulate the radius value on each curve, and if the total is 0, then we won't use it basically. Otherwise, we will. So if the radius of the curve of the entire curve is 0, we'll use 1 for the radius, and otherwise we'll use the radius of the curve. So that's just a safety feature basically. So then if we look at our curve here, we need to map the axes of our straight array along the x-axis to the curve. So along the curve we have the x-axis. That's pretty simple. But then we need to figure out what to do with the z and the y-axes in this case. And so we want one of those to map to the normal of the curve, which is going to point perpendicular to it at any point. And then if we take the tangent of the curve, which points like parallel to the curve at any given point, we can take the cross product of those two vectors to get a vector that's perpendicular to both of them. And then this normal vector and the cross of the two will be mapped to the x and z axes, or sorry, the y and z axes in this case, whichever the axis, the two axes that aren't whatever you selected as the aligned axis will be mapped to those. So the way we do that is by making those two vectors. So we already have the normal here. It can be used as is, and then we take the cross product of the tangent and the normal. We're going to scale those two vectors by a value that's based on the size of the input mesh. So we need to calculate that. This is where it gets kind of messy, because depending on what we have selected, we need to know the original size of the mesh. So that's from our normalized geometry, that size that we captured, the original position. So if we're using the x-axis, we want to use the y and the z. If we're using the y-axis, we need to use the x and the z. That's what these index switches are for. They're sort of messy, but it's just picking the two axes that aren't the aligned axis, and we have different combinations depending on which axis was selected. So that gets us the whichever size value is relevant for us, and then we need to do the same thing, but for the current position, minus 0.5, because this normalized geometry starts, the origin's like in the corner. So by subtracting 0.5, we essentially move the origin to the center. So then we take those two values, we're going to multiply the factor 0 to 1, or negative 0.5 to 0.5, that is the normalized geometry, by the original size to get the value that we should use for the offset. And then we're going to scale the normal and cross product of the normal and tangent vectors by those two values. So the one value was originally measuring how far along the y-axis of vertex was positioned, and the other was measuring how far along the z-axis of vertex was positioned. We've now scaled the normal and cross product of the normal and tangent vectors by those two values respectively. And then we can add those together to get the offset position from the curve that we want. And then if we scale all of that by our radius value, we can shrink or expand it depending on the scale that we've set. Then all we have to do is take our normalized geometry here and set the position of it again. This time we want to set the position to the position on the curve with an offset that's the vector we calculated using the normal and the tangent vectors. And that gets us this right here. You can see you can tilt or twist the curve and all of that. You can change the radius, and it arrays the mesh along the middle part along the curve. And that's it for the node group, really. Then there's just the merge by distance. If it's greater than 0, merge by distance, otherwise don't. And then we check if there's anything in there. That's so that if you don't have anything plugged in, it'll tell you. Check your modifier settings rather than just being an invisible object you can't select. I assign a random value because all of the strand modifiers do that, so that you can use the random attribute in your shader. And then we're going to append this geometry that we created to the control curve and anything else that was in the mesh previously that we did not select. So that way you could say come over here to these here and have this custom mesh applied only to the sagged part or whatever. And that is an overview of this new modifier I made and how all of the strand modifiers in general sort of are structured. Hopefully it was possible to follow that. I know I went over a lot really fast, but feel free to ask questions if I left anything out, because I know I skipped over some of the nodes a little bit. Anyway, that's all I've got for this one. The new update to the Strands library is up right now. You can go to Blender Market or Gumroad. If you already have it, the download's available. Or if you haven't heard of it before, I'd recommend going to my website, danielhickox.com. The links for all of that's in the description. And on my website, there's information about all of the modifiers for the strands and all of the different tools that I've made. you can see what all it can do. But yeah, that's all I've got for this one. Thanks for watching.